Hey folks, today we're going to talk about nuclear decay. This is our second podcast in this unit, so we're just going to focus 100% on decay in this one. Remember Henry Becquerel, and he looked at this rock, uranium, and the rock went and was decaying, and when it decayed, it went and gave off some kind of particle that went through the paper and exposed the photographic plate. Well, let's talk about what decay actually means, right? What does decay mean? Well, think about decay. Decay is going to be giving off some kind of particle. It breaks apart, kind of like wood rotting, except that's chemical, but the concept is still the same. It's changing. It changes all by itself. You don't have to do anything. So one thing it gives off is it gives off alpha particles. And you'll notice this symbol for alpha. Right? That's what it gives off. Now, where does it come from? Obviously, it comes from the nucleus. All right? All of the things we're going to talk about are coming out of the nucleus somehow. Well, what is it? Well, it has a charge of +2. Now, remember, because it's coming out of the nucleus, it doesn't have any electrons. All right? And what it actually is it is two protons, and two neutrons. So if I think of this, it's going to have a +2 charge, and it's going to have a mass of 4. So I would write it this way: 4, a mass of 4, a charge of +2, and it's an alpha particle. Wait a minute. 2 protons and a mass of 4. What does that sound like? Sure, it sounds like helium, right? Helium has a mass of 4 and it has 2 protons. So what's the difference between these two things? Well, the difference really is that there are no electrons. Here, we tend to have electrons. When we say helium, we assume that there are 2 electrons there, and when we have an alpha particle, we know there are no electrons. Well, when we are doing nuclear equations, we might actually write it this way. Normally, the most proper way is to write it as an alpha particle, but some people will write it as 4 and 2 helium, right? Now, when you do that, you just have to remember that there are no electrons with it, all right? So when an alpha particle hits you, how much damage does it do? Well, it has a very low penetrating ability, all right? Your clothes will stop it, right? For all intents and purposes, compared to some of the other particles that can be emitted in nuclear radiation, this thing is big and fat, and it's slow, and it's going to hit things, and it's going to stop. All right, so your clothing will stop it, a piece of paper will stop it, etc. Those types of things will stop it from hurting you. So alpha particles will hit your skin, and you go, okay, it hit the top layer of my skin. The top layer of my skin's dead anyway. Who cares, right? And frankly, that's the way you can look at alpha particles. They're not going to do much damage to you. All right? So that tells me, if we go back to Becquerel, that that piece of paper would have stopped alpha particles. So alpha particles were not exposing the photographic plate. So what could it have been? Well, it could have been a beta particle. Now, where does a beta particle come from? Well, this is kind of cool. A beta particle has a charge of -1. All right, thank you. All right, it has a charge of -1. Let's put that down here. It has a charge of -1. What do we know of that has a charge of -1? Of course, an electron. So a beta particle is an electron. Wait a minute. But it comes from the nucleus. There are no electrons in the nucleus. Well, you're kind of right there. So what actually happens? Well, if we have a neutron, all right, remember that a neutron weighs about 1 atomic mass unit, as does a proton. But a neutron has no charge, and a proton does have a charge. So what we surmise happens is a neutron breaks apart into 2 things. It breaks apart into a proton, which of course has a positive charge, and an electron, which has a negative charge. Now, this electron comes shooting out of the nucleus at a very high speed, leaving behind a proton, right? Well, when that happens, obviously you are gaining a proton in your nucleus. So you're changing from one element to another. right? So we will write this a bunch of different ways. We can write it as 0 with a -1 charge because it has virtually no mass. It does have mass, please remember that, okay? But as far as compared to a proton, it has very, very little, and we could write it that way. We could write it as 0, 1, and the most common way to write it is as a beta particle because it's a 0 with -1 charge, beta particle, right? We can sometimes write it as E-. I don't tend to like that. I tend to make sure that you know that it's a beta particle because this isn't one of the electrons that's just running around the nucleus. Now, eventually it will run around some nucleus, but right now when it comes shooting out, it's not running around it's not running around in the electron cloud. It's just coming out completely as a free electron. All right, so its penetrating ability, it's moving very fast. Okay, remember that for something to have the same amount of energy, an alpha particle, because it's big and fat and weighs thousands and thousands of times more than an electron, is moving much, much slower. So an electron is going to move extremely fast. It's a very high-speed electron, right? And it's very, very small. So this will actually go into solid material 1 to 2 millimeters, right? And that includes you. All right, so it will go through your clothing, it'll pass through a couple of pieces of paper, and it will go into your skin. So it'll go 1 to 2 millimeters into your skin. All right, and so it can damage your skin. All right, and this is the type of radiation often that is used in cancer treatment. All right, and we'll talk about that in another slide. All right, but this is like 100 times more damaging than alpha particles. Right? Again, because it's faster and it has higher penetrating ability, etc. All right, and now we have gamma rays. Well, gamma rays are completely different because gamma rays, what is it? It's light. It has no mass. No mass at all. Unlike an electron, which has some, and a proton, which has a lot, okay, light has no mass whatsoever. All right? It is not a particle. Not a particle. And it often accompanies, 2 C's, P-A-N-I-E-S, accompanies alpha radiation and beta radiation. Okay? So it's often with it. So anyway, now, alpha ray, it has no charge, and its symbol is what you see above you, which is a gamma. All right, but it has no mass and it has no charge, so it's a 0, 0. All right, and by the way, that's one of the reasons we're going to kind of just gloss over gamma rays. We're doing it here, but we're not going to talk about it anymore because it's hard for us to track because it has no mass and no charge. Now the problem is its penetrating ability is ginormous. All right, so it will not only go through your clothes, it'll go through you. Okay. It will actually go through us and come out the other side. All right? It goes in, it does some damage, and it goes out the other side. It doesn't stop. All right? Now, it can be stopped by, let's say, 3 meters, which is almost 10 feet of concrete. Or most of it can be. All right? Or a lot of lead. A few inches of lead. Right, so this stuff is really, really damaging, and so we don't mess with gamma rays. That's something you don't want to mess with because that stuff is really damaging. Okay, so now we have one more thing to talk about, which are positrons. All right, and these are our symbols for it up here, which look kind of goofy. Right. So what is a positron? Well, again, we're going to gloss over this one because it is so strange. But what it is, it's a positive electron. Think of it that way. Wait a minute, a positive electron? No, electrons are negative. Okay, well, what happens is a positron is when you have a proton. Where does it come from? It's a proton, and it breaks apart into a positron, or a positive electron, and a neutron. That's T-R-O-N. Anyway, You say, wait a minute, but a neutron broke apart into a proton and an electron. This doesn't make sense. And frankly, guys, it doesn't make sense. All right, this is well above the scope of our chemistry class. But I thought it might be interesting just to let you know that it exists so that you could see what the symbols were and kind of get an idea of where we think it comes from. All right, this thing has a +1 charge, but again, remember, it's just like an electron. It's really, really, really tiny. All right, so it has a +1 charge and acts like an electron. Now, how much penetrating ability does it have? Well, frankly, not a whole heck of a lot. And the question is, well, why not? Why wouldn't it have the same penetrating ability as an electron? Well, in theory it would, but what would happen if you take a positive electron, and a negative electron, because they're negative electrons all over, and get them together? All right? Well, when they get together, they actually annihilate each other. And that's what is really, really interesting. Okay? So what they do is they will hit each other and they will completely, 100%, go away. And they create a couple of gamma rays and a whole lot of energy, as in heat. All right? And they disappear. So positrons are really kind of just absolutely incredible things. You don't mess with those either because they generate a huge amount of energy. All right. Now, where in the world does this come from? How does this happen? Well, it happens if you have way too many protons, more protons, and fewer neutrons. Remember that when we were talking about this in our previous podcast, we talked about stability. Typically, you want more neutrons than protons if you get into big elements. Other than that, you want 1-to-1. Well, if you have too many protons and too few neutrons, you can produce positrons where a proton reverts back into a neutron. So that's kind of interesting stuff. Again, way beyond the scope of this class, but something for you to be aware of. Okay? So, do we ever see a positron? No, we don't. All right. And this is what I just said in the last podcast, where we generate a huge amount of energy when the positron and the electron hit each other. How much energy? The mass of the two electrons times the speed of light squared gives you the number of joules of electrons, joules of energy you get. Absolutely huge stuff. So here's an example of when a positron is formed. We have potassium, and it breaks apart, and one of the protons disappears, and you only have 18, and it puts off a positron, and here's your positron right there. All right, just to kind of give you an example. All right, why do we call these things decay? Well, you're looking at it. Here's a banana, and it decays. All right, well, that same concept is true. It's called decaying because it happens without any intervention of us. All right, it just decays. So when an atom emits alpha, beta, or gamma radiation, or frankly positrons, it's said to be undergoing radioactive decay. Why decay? Well, the original nucleus decomposes or decays to form a new nucleus, releasing radiation in the process. We did not do anything to make that happen. It is spontaneous. Now, the nuclear equation keeps track of the reaction's components. Now, we talked about how mass is lost, but it's a very, very tiny mass, and it's not something that we're going to measure when we look at these types of equations. All right, so let's look at alpha decay. Let's look at nitrogen-16, right? And if we look at nitrogen, the protons are the kind of orangey things, and the yellow ones are neutrons. And we're going to draw alpha decay. Well, alpha decay is the loss of 2 protons and 2 neutrons to make a total mass of 4. So potentially, I could take these 4 guys right out of there, and they become a beta. They become an alpha particle. All right, and so what are you left with? Well, let's look at what we're left with here. We have 1, 2, 3, 4, 5 protons, and we have 1, 2, 3, 4, 5, 6, 7 neutrons. 7 plus 5 is 12. Right? So we have 5 protons and 7 neutrons. And if we look at number 5 on the periodic table, we find out that that is boron. So this is going to be boron 12. And so we got a 4 and a 2, which is an alpha particle, And you'll notice the 4 and the 12 add up to 16, and the 5 and the 2 add up to 7. So that started as nitrogen, because number 7 is nitrogen, and this started as nitrogen 16. And it broke apart all by itself, no intervention from us, into boron and an alpha particle. Okay, so that's exactly the way we would write this, as alpha decay of an isotope of nitrogen, excuse me, starts as nitrogen. It's number 7 on the periodic table, meaning it has 7 protons and has a mass number of 16. Now you'll notice that the 16 up on top adds up to the 12 plus the 4. And the 7 on the bottom adds up to the 5 plus the 2. And that's the way this is going to work. And you say, well, wait a minute, I thought you said we lost mass. Well, you did, but it's a very, 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 very tiny amount of mass that was actually converted into energy. Nuclear equations balance. For purposes of what we're doing, they are going to balance. So what I'd like you to do is see if you can try polonium. If you don't feel you can, I'll do another one for you, but pause the video, see if you can do this on your own. All right, so we have polonium. And it tells us that this isotope of polonium weighs 210. Right? And we look on the periodic table and we can find out that polonium is number 84. Now, we've said that it decays and it goes through alpha decay as a process. So let's go and put our alpha particle here, which we know has a mass of 4 and has 2 protons. Remember, there are no electrons. So what has to happen to make our numbers on the top be 210? Well, if this is 4, this number on the top has to be 206. And our number on the bottom has to be 82, because 82 plus 2 gives me 84. So I get 206 and 82, and if I look on the periodic table, I have just produced lead, Pb. All right, because Pb is number 82. Right? That's alpha decay for polonium 210. So you should be able to do those. All right, let's look at beta decay. Let's assume that nitrogen went through beta decay. So what happens? Well, when it goes through beta decay, we're going to take one of these protons here. Sorry, my bad. Let's try that again. We're going to take a neutron. And the neutron is going to split apart into a high-speed electron, which comes out here. And it changes from a neutron into a proton. So what happens? We have 1, 2, 3, 4, 5, 6, 7. Now we have 8 protons. Right, we have 8 protons. And we have, let's see, we have a total mass. Well, the mass hasn't changed. It's still 16. So we have 8 protons. So 8 protons, if we look 8 up on the periodic table, that's oxygen. And what happened was we lost a high-speed electron. Now, how do we write a high-speed electron? Well, we write that as beta with a -1 and a 0, just like this. All right? So we'll notice that 16 plus 0 gives us 16, and 8 minus 1 gives us 7. 7 is nitrogen. We started with nitrogen 16, so that should make sense. That's beta decay. Right? Remember that beta decay is giving off a negatively charged electron, very high speed, and so that's why we write it that way. All right, so that's our final equation for the beta decay of nitrogen 16. So let's try it. You try going through beta decay of carbon 14. Pause the video, see if you can do it. All right, so we have carbon. It has a mass of 14, and carbon is number 6. Carbon 14 is used in radioactive dating, and we'll talk about that in a future podcast. So let's see, if we take carbon 14 and we give off a beta particle, well, a beta particle has virtually no mass, and it has a -1 charge, so I have to add a -1 to a 7 to make a 6, and the 14 hasn't changed, so that is nitrogen. So that tells me that carbon 14 is going to decay into a beta particle and nitrogen. Very interesting. So carbon, what does carbon look like? Carbon's a solid. It's kind of a black solid. It looks like pencil lead. Frankly, it is pencil lead. All right. And what does nitrogen look like? Well, nitrogen's a gas. So that tells me that this solid is literally turning into a gas and disappearing into the atmosphere. How cool is that? All right, nuclear equations balance. Remember, they've got a balance. We got a couple, actually 4 problems for you to do. So pause the video and see if you can do the alpha decay of uranium-233. Did you pause it? Okay, here we go. Uranium weighs 233, and it's number 92 on the periodic table, and it decays. It breaks apart all by itself without any help from me into an alpha particle, which is 4 and 2, and remember, my numbers have to balance. So 229 plus 4 gives me 233, and 90 plus 2 gives me 92, and this is the element thorium. How do I know it's thorium? I look up number 90 on the periodic table, and that tells me it's thorium. All right, how about the beta decay of potassium-43? Again, pause the video, see if you can do it. All right, so we have potassium, which is number 43, and it has a mass of 43. It's number 19. Now we have beta decay. Beta decay, if you remember, has virtually no mass, but has a -1 charge. So that means my number on the bottom has to be 20. My number on the top remains 43. Number 20 is calcium. So that's the element that I have there. That is the beta decay of potassium-43. All right, we're going to go on to the alpha decay of gold. Oh, that means it's not going to be gold anymore. What a bummer. All right, so go ahead and see if you can do the alpha decay of gold 185. All right, if I look at gold, gold is number 79 on the periodic table, and this has a particular mass number of 185. I sure hope the gold in Fort Knox isn't this isotope, or else it's just going to disappear and become something else. Well, what's it going to become? Well, it's an alpha particle with a 4 and a 2. So let's see, that means the bottom number would be a 77, and the top number would be 181. And if I look up number 77 on the periodic table, that is iridium. Who in the world wants iridium? I don't want iridium. All right, this is the last one we get to do. Go ahead and see if you can do francium-233. Pause the video, give it a shot. All right, here we go. We got francium. It's 223. And francium on the periodic table is number 87. And when we break it apart, we have a beta particle, which is a 0 and a -1. And that means our top number did not change. It's still 233. And our bottom number has to be an 88, because 88 minus 1 is 87. And we produce, the thing that we produce is radium. All right, you should be able to do those, folks. There's a worksheet that will give you some practice. So if you do that on the worksheet, that would be fabulous. And see you in class if you have questions. Have a good one. Bye-bye.